As a global company, we hear people say VIAVI in a lot of creative ways.
VIAVI VIAVI.
It could be because our name is comprised of a lot of vowels. Or, if you were to turn it upside down, it's sometimes hard to figure out the right way up.
Lavia.
We used to be JDSU, but today VIAVI is recognized around the world as a leader in telecommunications and optical solutions with millions of installs. We may have a funny name, but our award-winning test solutions are no joke. They're everywhere, helping our customers enable the next generation networks that connect the world. But wait, there's more. We're also a leader in optical technologies. At VIAVI, no matter how you say our name, we hope you remember us as the company that you rely on for your telecommunications and optical technology needs.
VIAVI.
VIAVI.
VIAVI!
VIAVI.
Take a look around you. We live in a massive, complicated, and highly connected world. To keep up, businesses everywhere work to deliver new services, enhance operational efficiency, and deploy technology that saves time and money. With all of this going on, do you sometimes wonder where you fit in, the value you bring, how you can take control and command the network, or at least you're part of it, to help your business thrive? The people of VIAVI believe that everyone deserves to be the hero of their own story, and every hero needs a committed sidekick to help them succeed. Whatever your role, leading, supporting, implementing, it is likely that you were either installing network components, hoping that it's done right, the first time, every time, or playing detective with intelligent software to identify hidden problems in your network. That's where VIAVI comes in. We provide the intuitive instruments, systems, and technologies that you can use to command the network. VIAVI has a very impressive history. With our global network of amazing partners, we offer tested and proven solutions in over 137 countries across 30 different market segments and are recognized as global leaders in 5G, fiber, 3D sensing, and more emerging technologies. VIAVI is a recognized industry leader in every category. But don't take our word for it. These industry awards speak for themselves. We excel in listening to you, sharing best practices, and delivering proven solutions to meet your business objectives. You know, everything you expect from a committed sidekick. For every role in every business everywhere in the world, VIAVI helps you deploy solutions that let you take control and deliver more value in your role and for your business. A great first step in discovering all that we can offer is through the VIAVI Solutions Locator tool. It's free, fun, and easy to use. Check it out and see where we can help you on your journey to be the hero and command the network.
Light is vital for life. And light is at the heart of everything we do at VIAVI. Our technology works at the speed of light, and we're lighting the path to the future for our customers.
As service providers are handling more services and access technologies, from fixed line to HFC to 3G and 4G, they need increased automation in the network to provide the best quality of service. VIAVI is enabling that today by connecting and visualizing data from all parts of the network through software and instruments. Only when you can see all the parts of the network and different access technologies as we do, you can create intelligent workflows and automation that will make managing a network simpler and more reliable.
VIAVI is the leader in 5G testing. Our solutions have become the de facto standard in 5G testing labs, where we are enabling mobile operators to test 5G call and data quality from the network to the subscriber. As 5G becomes a reality, it will open us up to new possibilities that we never dreamed of before.
Multi-place service providers across the globe are pushing for gigabit internet speeds to satisfy the ever-increasing demand for data-intensive services and applications. That's internet delivered 150 times faster than the global average. The technology can be fiber, coax, copper, and even mobile, but the requirements are the same. They need to provide the best possible quality of service, and they need to automate the provision, assurance, and optimization services as much as they can. This goes from labs and data centers to the core network, even through the technician home visits. Currently, we estimate that around only 4% of the global population has access to gigabit internet. This is increasing every quarter, and we are excited to be part of it.
We are lighting the path to network automation, gigabit internet, enterprise data centers, 5G, avionics, tactical networks, 3D sensing, and to the future. The world is getting faster, and we're with service providers, enterprises, and manufacturers every step of the way to make that evolution as easy as possible.
.5G promises to deliver enhanced mobile broadband, ultra-low latency, and machine-to-machine communication on an unprecedented scale. Many industries will benefit from this new mobile infrastructure, from connected cars and smart cities to healthcare, energy, and public safety. All of this requires a completely new network architecture to support the many services and applications that often have conflicting needs. This new 5G network architecture will be highly disaggregated, virtualized, automated, and programmable. Intelligence will move to the edge to support low-latency applications. In 5G, the RAN is the new core. In order to manage, assure, and optimize this new 5G network, solutions will need to be more accurate in location, more programmable, and be beam-aware and 3D-aware. By delivering validation, verification, and visibility, VIAVI supports all stages of the 5G lifecycle, from lab to field to assurance, and there are connecting capabilities. In the lab, we are the leading provider of end-user experience simulation and testing. When it comes to installing and maintaining the network in the field, VIAVI was first to market with 5G RAN performance testing, coupled with extensive fiber test tools.
Welcome everybody. We have Mike from North Carolina and Jeff from Texas for our Understanding OTDR Basics webinar. So for our agenda, Understanding OTDR Basics, simple class but good enough for everybody to understand how they work. How does an OTDR work? We have understanding the mystical launch cable length. Does it exist? How long is it supposed to be? We have many different answers in the industry, and today we're going to cover numerous situations. So if somebody wants to use a certain length launch cable, we can understand why they are requiring it. Then we have analyzing OTDR traces using the VIAVI SmartLink mapper. We'll talk about how to get exact distance to faults, and then we'll sneak in some tips and tricks that'll help novices and experts, and then we'll be taking Q&A as well. So in our slide deck, we start with OTDR theory. How does the OTDR work? It's like a radar. Police shoot radio wave at our vehicle, bounces back, we're speeding. We're not speeding. They can shoot a laser at a vehicle, laser bounces back, they got our speed. Airport people shoot a radio wave in the sky, bounces off the airplane, and we can see how high that airplane is. And weather people have radar too. It hits the cloud, comes back, and the weather people tell you it's a 50% chance of rain. For our outdoor folks, it's like a fish finder. Shoot a radio wave in the water, hits some fish, bounces back. And if we got any submarine people out there, same thing there. Sonar hits a submarine, bounces back, bats echolocate. And that's what the OTDR is doing. It shoots down a pulse of light, waits for it to come back, and it does it several hundred times a second, if not into 1,000 times a second. The OTDR only measures two things. One is backscatter, the other is reflection. So the concept of Rayleigh backscattering is when light goes into a fiber, it scatters in all directions. The OTDR is seeing the light that is coming back to the source. Reflection is a Fresnel reflection. We just call them reflections. When the light hits a glass-on-glass connection, then it causes a large amount of light come back to the OTDR, and the OTDR detects that. And then from there, it tells us what's out on the span. So for the next slide, I made this very simple, no trace, no dBs. We see a line going from the upper left to the bottom right, and that's the OTDR measuring the backscatter. It varies by wavelength, but that's an actual measurement. That's what lets the OTDR work. If I shoot a flashlight at you and back up, it gets dimmer and dimmer. As that light goes down, the light is getting dimmer and dimmer, and the OTDR is seeing it. Then at the very beginning, there's a spike, and at the end, there's a spike. So a spike is a glass-on-glass connection. So at the beginning, we have glass on glass. At the end, it's glass to air. So we see a reflection, and then we see the noise of the machine. So with that information right there, we all now can read an OTDR trace. Pulse width is the amount of light that is sent down the fiber. The OTDR selects it either via time, such as 10 nanoseconds, or via distance, or both. If we're not OTDR experts, I always say auto is my friend. Let the OTDR automatically pick the settings for you, the user, and it will get the right amount of light. If we're going to go down a span real far, we need a lot of light. If we're going on a short span, we need a little bit of light. So in pulse width 1, we see a straight line, some dips, some reflections, and that's a good pulse width. In pulse width 2, it doesn't start out as a straight line. It already starts out as long grass, then it goes to weeds, then there's a big loss, and you see that the squiggly lines is getting worse and worse and worse. That's not enough light to go all the way down to the end of the fiber. OTDR experts will select pulse width themselves, but if we're not an expert, OTDRs today have an automatic mode. It's going to pick the correct optical settings for you. So now that we know the OTDR is looking at backscatter and reflections, it can get the loss of an event. So in the left picture, we see a straight line, a dip, and a straight line. Well, that's loss with no reflection. Most of the times that's going to be a fusion splice, but it could also be a bend. And later we'll show you how to tell if it's a bend or a splice. In the right picture, we see a connector. We see the signal before, a reflection and a loss, and then we see the signal after. So what causes a reflection? It's a connector, such as a UPC plugged into a UPC, or a mechanical splice. But typically there's more mechanical connectors out there, Sam Charlie to Sam Charlie, etc., than there are mechanical splices. So when can an OTDR not measure loss? On the next slide, the OTDR must see the signal before and the signal after. That's that straight line. Well, in the picture with the OTDR, we don't know what the OTDR output power is. This is a test laser. It's not going to be exact every single time. So we can see the reflection and the signal after, but we don't know the signal before. So at the beginning of the OTDR, we don't measure loss. That's a dead zone. At the end of the fiber, we see a spike. That's the reflection hitting air or hitting the connector that's terminated at the end. And then The noise floor appears, that's the noise of the machine. It means that's the end of the fiber. The other scenario is when events are too close together. There's a blind spot or a dead zone, and Jeff will talk about that. But there's two connectors there in that picture, and we see the signal before the first connector, but in the second connector, it's too close to the first one. There's still reflections coming back to the OTDR, so we don't see the signal after. After the second connector, which is the red marker, we see signal after, but we don't see the signal before. So the OTDR can see the loss across those two connectors because we signal before and we see signal after, but it's not going to report the loss of each of those connectors because of dead zones or a blind spot. Now Jeff's going to go and do some dead zones, and then once we're done with these slides for the OTDR optical time domain reflectometer, we're going to show you a bunch of traces on some machines. That way it saves time so we don't have to shoot traces all day, but we'll also do some live traces for you as well.
Thanks, Mike. Thanks, Mike. Okay, so Mike talked about dead zones, and there's two types of dead zones. There's an attenuation dead zone and an event dead zone. Well, attenuation dead zone was what Mike was just talking about. We saw two events. We saw the beginning of one event, but we never saw it return. And then we saw the second event, and then we saw the return after that event. So if you look at a dead zone, it's the minimum distance of a reflective event to a non-reflective event that can be measured. So in the next slide, I'll show you, but we're not going to go there yet, what we're talking about there. An event dead zone is where we miss events. So event dead zones are typically caused by launch pulses. I might be shooting a 20 microsecond launch pulse, which is 2 kilometers long. I'm going to miss everything in that first 2 kilometers because that launch pulse is so long. So how do you get through dead zones and things like that? It's really adjusting your pulse widths. And Mike's going to talk about smart acquisition and things like that later on, how we can measure the events up front and measure the events in the back and put them together. So on the next slide, we can see that attenuation dead zone. Now, the way I always like to report dead zones and loss and things like that is we talk about a signal in and a signal out. So think about yourself being in a dark tunnel. I have a flashlight. I'm going to turn it on and off three times, 1 second at a time. So it goes light, dark, light, dark, light, dark. You saw all 3 pulses. Now, let's say I hit that flashlight twice real quick and went boom, boom. And your eyes and your mind said, I saw those 2 pulses, but I never saw it get dark between those 2 pulses. And that's the example that you see on the screen there. I hit you twice with it. I saw the signal come in, but I never saw it get dark between those 2 pulses. So that's a good example of a dead zone. Now, if I have an event dead zone and I come in there and I hit you with a bunch of pulses, I hit you with 10 pulses rapidly, boom, 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 boom. Then you're in your mind saying, wait a minute now, I saw a bright light, I got blinded by it, and I've missed this. So dead zones are out there. A lot of times short jumpers can cause dead zones. And again, adjusting your pulse width can help you overcome those. Next slide. So when it comes to OTDRs, I call this the key or the holy grail to understanding OTDRs. It's the OTDR cheat sheet I put together. OTDRs are predictable. Everything that you see out there with OTDRs, as long as you have clean connectors and things like that, everything should be pretty much predictable out there. Now, we use smart icons, and I'll talk about those in just a little bit, but we have icons for the beginning of an OTDR, for the end of an OTDR launch cable, for splices, for connectors, for bins, for the end of the OTDR, things like that. But really, the key to understanding everything is, what do my numbers mean? What do my loss and my reflections mean? So when you look at loss on a fiber or attenuation, if we look at single mode fiber, you can average it out to be about 0.2 dBs per kilometer at 1550, about 0.35 dBs per kilometer at 1310. Now, some folks will say, well, my newer fibers, I'm getting 1.8 or 1.7 something. Sure, But on the older fibers, you're probably getting 0.2 something. So it's just easy for me to keep easy numbers in my head. I say 0.2 dBs per kilometer at 1550. Same thing if you look at single mode fiber, 1 dB at 1300 nanometers, 3 dBs at 850 nanometers. When we look at splices, so we come down and we look at splices. The newer fusion splicing machines might say, hey, this is a 0.05 splice. That's phenomenal. The older fusion splicing machines might be 0.1 or 0.2. Depending on which spec you're using, if you're using one of the TI specs or using one of the ISO specs, it could be up to 0.3. So 0.1, 0.2 dBs is still a very, very good splice. The newer splices, again, might be 0.02, might 0.03, 05, or something like that. When your fusion splicer tells you, hey, this is a 0.05 splice, it's running an algorithm and it's making its best guesses. We think this is really good. You won't know the true loss until you look at it on an OTDR or on a loss meter. So if we look at connectors, we've got UPC connectors, APC connectors, we've got mechanical splices and things like that. The rule of thumb is for a connector 0.25 to 0.5 dBs per kilometer. Again, some of the TI and ISO specs might say 0.75. So if you're looking at connectors and you say, hey, I have a UPC connector and it's somewhere between 0.25 and 0.5, and I have a mechanical connector which might be 0.15 to 0.3, if you looked at the OTDR, could you really tell the difference? Hey, this might be a mechanical connector. This might be or mechanical splice. This might be a regular connector. And the answer is probably when you look at the loss values on the next page that we're going to go to in just a second. So everything out there has a value. Once you understand these values, OTDRs become very, very simple. Now, if you have splitters out there, if you have a 1x2 splitter, you're going to have somewhere around 3 dBs. As you double those splitters, this is not linear, this is logarithmic, you're going to go up by 3 dBs. If you cut the splitters in half, you'll go down by 3 dBs. I like to keep a 1x32 splitter in my head. I know it's 15 dBs. Might be 15 to 17, but the easy number says it's 15 dBs. If I cut that 1x32 in half and go to a 1x16 splitter, I've got 12 dBs. So again, OTDRs, if you're telling them to look for splitters in a PON environment, it knows what these numbers are. It can figure out the splitters. Now, again, we have smart icons up there. So we have smart icons for splitters where our OTDR will tell you this is a 1x8 splitter. This is a 1x32. If you have muxes out there for CWDM or DWDM, we can pick up those muxes and demuxes with those smart icons. Next slide. So now when we've just looked at our loss values, let's look at our reflection values. So if I look at a blue UPC connector, so whether it's a UPC, whether it's an LC connector, if it is plugged in clean, it's plugged into another connector, I'm going to see something around -50 to -55 dBs. It might be a little bit higher, might be slightly lower, but I always say it's in the -50-ish range. So if I look at my OTDR and it's in the -50s, I know that I have a UPC connector that is connected clean. If I have a green APC connector and that's plugged in clean, I'm going to see something right around a -65, maybe up to a -74. Could be down to a -63, but it's going to be somewhere in that -60 range or -65 to -70-ish range. If I look at a mechanical splice, mechanical splices are somewhere in the -40 to -50s. I always say something in the -40-ish. So if I went back to the previous slide and I said, well, a mechanical splice is 0.15 to 0.3 dBs, and I've got something for my loss in the -40s, I'm going to hinge my bet that's probably a mechanical splice out there more times than not. Now, if I have a UPC connector, remember that blue connector, whether it's an LC or SC, whatever it is, if it's unplugged and open to air, so now I'm glass to air, I'm going to be somewhere in the -14 to -20-ish range. So that just tells me, hey, I've got UPC connector and it is open to air. If it's plugged in clean, again, it's going to be in the neg 50s, neg 50, neg 55. There's something in that range. If I've got an APC connector and it's open to air, I'm going to have something around neg 35 or less. It might be neg 40, it might be neg 45. You know, it just depends on that APC connector. So I can always tell by looking at my OTDR, really sometimes, you know, most times, what type of connector I have out there, and is that connector plugged in? Now, if I look at fiber breaks out there, I might see at the end of that fiber where Mike was talking about we go into the noise, I call it we drop off into the grass and weeds. If I look at a fiber break, I might see something in the neg 30, maybe all the way up to neg 48. Commonly, it's around neg 42. But it's not carved in stone that way, but it's somewhere probably going to be in the neg 40s on that fiber break. Fusion splices, bends, have no reflections. So I'm only going to see loss on those. If there's a bend on the fiber, you're going to see this here in just a second. Bends are typically 5 times worse at 1550 than they are at 1310. In the OTDR basics that we talked about in our first YouTube presentation, I talked about bends. And a lot of technicians will go out there and they'll say, well, I'm going to shortcut this. I'm only going to run one wavelength. Maybe they run 1310. Well, 1310 is never going to pick up those bends. Or they might say, I'm only going to run 1550. You know, I just want to run one wavelength. I don't want to take the time to shoot the other one. And now 1550 just by itself is going to show up as a bad splice if there's a bend on it, versus if you shot both a 1310, 1550, and the OTDR can compare the two. And now the OTDR can make that determination. There is actually a bend out there. So instead of going looking for a bad splice, you know you're looking for a bend. So when we look at OTDRs, this is really the key, understanding your numbers and things out there. So next slide. So we do have a poster out there. You can go online. You can download this poster. If you fill out the form, we will send you the poster. But all these numbers and all these icons and things like that and all these events that an OTDR, they're on that poster. Pardon me? Thank you.
And Jeff, can we just pause for a second? We have a very interesting question from Dan Reed.
Sure.
Yeah, the question is a launch cable required if you are only using the OTDR to get distance to the end of the fiber, not looking for loss?
No, you don't have to use a launch cable. And I'm going to hold off on that one and let Mike answer that one in the next round, because we're going to be talking about launch cables. So that's going to be Mike's thing after I go through the OTDR. So Evan, if you'll bring up my GUI, I've got an OTDR trace that I loaded here. So now we get to look at some of those numbers and things that I talked about. So if we look at event number 3, and I actually click on event number 3, down here in the left-hand corner, I've got an icon down here. If I click on it, it tells me a splice, and it actually tells me the threshold for that splice. Now, if I look at the loss, it says it's a 0.193. Remember, splices can be 0.1, 0.2, all the way down to 0.05. So I could look at the loss on that and pretty much determine, yep, I've got a splice. And then if I look at event number 4, I've got an icon down here. If I click on that, it tells me it's a connector. It tells me in this case, the thresholds we were using at the time, 0.75 dBs. So it's a good connector. But now my question is, can you tell if it's a UPC connector or an APC connector? So remember when I talked about, when we looked at reflections, and I said a blue UPC connector connected clean would be somewhere neg 50, neg 55-ish, you know, somewhere in the neg 50s, and an APC connector might be neg 65 to neg 70 something. So if I look at this, it's a neg 68. I can tell that that is a green APC connector, and it is connected clean. It's got good loss. If I go down here to the next one, I've got this bend icon here. It tells me there's a bend on here, and it says it's a 1.698. Well, up here in the top, I'm actually looking at 1550. I'm going to change this to 1310 up here on the right. I'm going to click on up here on the right. I'm going to click on number 1, and I'm going to go to 1310, and event number 5 is showing up, it looks like a splice at 4216 for the distance. If I click back on that, it says, at 4216, it's showing a bend there. So 1310 is looking almost like a splice because of the loss that's on it, 0.231. But if I look at the bend there, the bend is 1.698 or 1.7. That is well more than five times more loss at 1550 than it is 1310. Now I'm going to do a quick zoom here on event number 5. So I'm going to zoom in here. I'm going to do a quick zoom. And now if we look at the trace that's in blue there, that is actually 1310. And that is showing a very little loss, very small drop. It's hard to see because of the cursor there. I'll take that cursor and kind of move it over here a little bit. Move that cursor over a little bit. There we go. And go back to my zoom feature here. But at 1310, I really don't see it. Now I'll put 1310 in green here. I'm going to switch over. And there's just a minuscule amount of loss right there. But if I look at 1550 here, and I put that in green, you can see that big 1.7 dB of loss that's on there. And the OTDR is able to recognize that as a bend. If I look at the end of the fiber here, event number 6, I don't have loss. And you know, the question I always like to ask my technicians is, well, shoot, why don't I have loss there? I've got a reflection. And remember, Mike told you we have to have a signal coming into an event and a signal out. On the OTDRs, I like to refer to it as a straight line in, straight line out event. If I go back here to the end of my fiber here, you can see that I've got the straight line coming in, the signal coming in, and it simply drops off into the grass and weeds. And now I've got a neg 50 reflection right there, which tells me this is probably a blue APC connector that is connected clean. So Mike, I'm going to go ahead and hand this back off to you. And Mike's going to talk about launch cables.
So we do have a slide on launch cable. I believe the question was launch cable. Well, I don't believe that exists. So we'll go over that scenario. But to me, there's two main reasons for a launch cable. One is to protect the OTDR. If you test 100 fibers, you don't want to plug into your OTDR 100 times. Plug in a launch cable once, test 100 fibers. Now, at the end of your launch cable gets fried, replace that launch cable, and it's going to be cheaper than sending into OTDR for repair. OTDRs have warranties, but in the same way, if we crack our windshield with a pebble in the windshield, that's not covered by insurance. If you get a new windshield, we're paying for it. The same way, if we permanently damage our OTDR, then that's not a warranty item. And even if we don't damage it, if it's got a mud pie on there, the OTDR might not be able to see it. So one, protect your OTDR. And the second is, we said we can't see the loss at the OTDR. If you plug the fiber under test directly into the OTDR, we don't know the loss of that front end connector. So now if we have a launch cable, we can move that front end of the fiber out of the dead zone of the OTDR so we can see the loss of the front end connector. So we'll give you some examples. Launch cable lengths vary by person, seniority. In the old days, we'd say 1,000 meters. Now we hear 50, we hear 150, we hear 20, we hear 10. So we'll talk about these different situations. But if you're going to use a long post width and you want to see the loss of that front end connector, and you're just going to do one shot, then typically you need to have about 3 times the length of your post width. So if you have a 1,000 meter post width, you're looking at a 3,000 meter launch cable to see that. So now we'll go and we'll screen share my OTDR so we can see some. I need to share that so you can see it, but I'm going to share my OTDR with you. Some of these we'll do live, and some of these we're just going to do static so we can save time. But the question was, can we see, or do we have to use a launch cable if we're just trying to look at the total length and look at the total loss? So the true and correct answer is no. Somebody like Jeff or me might say, you always got to have a launch cable. You always got to have a launch cable. Well, if you just want to check a span and you don't have a launch cable, I'm not going to wait 1 hour for Johansson to drive out there because he's the only one that's got the Frank Charlie APC, or excuse me, Frank Charlie UPC. We can just plug in and see the total length and total loss. So if we're going to work on a fiber, we're getting ready to turn up, or we just want to check, make sure everything is good. It was great 2 weeks ago, a little spot check. You can do it without a launch cable. So in this case, this is an 82,000 feet span. That's about 25 kilometers. That's about 15-ish miles. And the OTDR says there's only one event. This is a reel. So that's why there's no events, no splices. And it says fiber in. So if this is an 82,000 foot span, then we know that we got the correct distance and we got the total loss. And for advanced tip and trick, Jeff was talking about those numbers. You might have to get that poster if you don't have it memorized. But on my reel here, on my network, I have a UPC open at the far end. Jeff said it should be about neg 14-ish, 16, 18. Well, this is a neg 33. So I'm either plugged in dirty or we got a break. And sure enough, somebody closed a lid on the box. So there is a break. I don't see a neg 14, I see a neg 33. So what I would do if I think I'm broke, I'd have somebody plug in at the far end. And if this reflection at the end never changes, well, the OTDR isn't reaching the far end. You might be broke right at the boot of the connector, a couple inches away or a couple of feet away. A long pulse width, you're going to be in the dead zone and not see it. So if you expected a 4.9 dB loss and distance exact on this span, you're going to call it good, but it's not good at all because the end reflection is bogus. Had somebody shot from the other side, then they would have had distance 0 because we're broke right at the start of the span. So now we'll do another example of launch cables.
Hey, Mike, before you jump into that, we had another good question about launch cables from Luke, and he's asking about working with cell towers. Is it recommended to use a 10-meter launch cable, and is that even effective?
So it depends on your OTDR. If you're shooting at cell towers, then it's very short. So you need a short pulse width. So we commonly use a 10 nanosecond or less. So that's a 1 meter pulse width. I said your launch cable needs to be 3 times the length of the pulse width to have a good attenuation dead zone. So in the old days, we recommended 10 meters. So now on our different OTDRs, we commonly recommend 20 meters, but on a short span, you can shoot 1 pulse width, see everything on the span, see the loss and reflection of the front end connector. So if 10 meter works on most OTDRs, it should, then you're just fine and safe. If you had a lower quality OTDR and that's going to be within a dead zone, then you still should be able to go with a 50 or 100. But the point of the launch cable is to see the loss and reflection of the front end connector. With our OTDRs, when we shoot up a tower or up and down a tower, the contractors go and loop back. Then we commonly use a 10 meter launch, a 10 meter loop back at the top, and a 10 meter receive cable on the bottom, and we see everything just fine. The other scenario in that case, and that's one of the scenarios, is you got the math and you say, hey, this is short. My 10 meter works, my 20 meter works, my 50 meter works, and your company or your customer says you got to use 1,000 or you got to use 150. And I told somebody just this week, hey, it doesn't got to be that long. OTDRs are better now. He goes, these guys will never change. Well, if somebody says use 1,000, you're using 1,000. On a cell tower, it might make your trace worse because you're going to have to crank up the pulse width because you might have 1,000 launch. 1,000, if you're doing a loop back, you're going to have something long up top and something long on the down fiber. So in a tower situation, we definitely recommend short as long as the OTDR can support that. Now in this case here, I do have a launch cable. It's 150 meters, but the OTDR doesn't see it. So remember what we said, if you have a long pulse width, then the OTDR is not going to see it. In this case, the post width is twice as long as the launch cable. We don't even see it. So on the last trace, this is the same span. It was, when I have a launch cable, right now my distance is wrong because I can't see it. It's supposed to be 82,000 something, and I got 500 feet of launch cable on here, so my distance is wrong because I'm blinded by the dead zone, and I don't even see that launch cable. So now we'll go to another one. In this case, I see the launch cable. It's 500 feet plus 83,000 feet. So it's a 150 meter launch cable. Post width is only 30 meters. So in this case, it's fine. Somebody may require you as a tester to use 1,000 meters. It's not needed at this distance. We're using 150. We just see it just fine. Now we have another scenario is, can we use a short launch cable on a long span? It's possible, but you do multiple post widths. So we'll do an example of that here. I will hit start. And this OTDR is not going to shoot 3 post widths. But when we shoot 3 post widths, we show you the trace from all 3 post widths. If you got a horrible trace, your map is going to be bogus. You see a second trace. So I'm shooting 3 post widths. I get 1 trace. I use the word stitch because we stitch them all together. And then we got 1 map and we got 1 trace. And Jeff's going to go over the SmartLink view, but now we can go into the SmartLink view and see all of these events. So in that case, I'm on a long span, but it says I got a 10 meter launch cable and we were able to detect it. If I'm on a long span and I shoot 1 post width, I would have been blinded and not seen this little jumper. So the downside is you increase your test time, but the upside is you get to see stuff with a short launch cable. Contractors commonly have to use a long launch cable, and then sometimes they're required to do a short shot. Well, if you want to do a short shot, we can do the short shot followed by the long shot automatically. And then now you get 1 trace, 1 file, you got a short launch cable, you fulfill the requirements of a short shot and a long shot, and it just saves you test time. Instead of doing 1 trace and a second trace, we do them both at the same time, save them in 1 file. How do we do that? It's with our software called Smart Acquisition Advanced. And if we have FTTH Slim got a lot of splitters out there, then we can use up to 6 pulses automatically. But if you don't have PON and you're just doing regular OTDR, if you have Smart Ac Advanced software, then you could do 2 or 3 pulse widths, get 1 map and 1 trace. So now we'll turn it over to Jeff. We explained in slides how to look at events and analyze them. He did the poster. He analyzed a trace, and now we're going to go do the easy mode for folks who haven't used OTDRs. SmartLink Mapper will analyze a trace for you.
Thanks, Mike. So when we look at OTDRs and we look at the technicians that are moving into optical stuff, they may have been coax RF technicians in the cable world. They may have been cable pair technicians in the telco world. And all of a sudden, one morning, the boss says, "Team, we're doing fiber." And they're like, "Here's all these new things. Go out there. Hey, there's a fiber break, or we're going to do a fiber install. We need you to certify this fiber." And people are like, "Boss, you just gave us this stuff." So what we did is we developed what we call the single mode smart test. So I'm going to click on this. And if I was to take a technician through the expert OTDR, they'll open up the expert OTDR. And we've got 5 pages of stuff that you can actually go in and set. And that'll just scare the dickens out of technicians. So now when you go into Smart Test, we've loaded 2 configurations for you. One of them is called Express. The other one is called Certification. Express uses 7-second acquisition pulses, so it's very fast. And that's really so I could, if I want to look at a span, I think there's a break or something out there, 7 seconds, I can go out there and take a quick peek. I can see what my loss is and I can see what my distance looks like. But it's not going to give me a very granular OTDR trace, depending on how long that span is. And then we have one called certification. A certification uses 20-second acquisition pulses. So I've got a test box hooked up and it'll work just fine on the Express. So I'm going to go ahead and load Express. And what we've really done here is we've taken the guesswork out of how do I configure my OTDR. So up top here, I have 3 wavelengths. I have 13, 10, 15, 50, and 16, 25. If I'm out in the field with somebody, I don't want to shoot just one wavelength unless I'm doing live fiber on a PON network and I'm shooting 16, 25. If I'm on a regular fiber network, I want to shoot both 1310 and 1550. I want to make sure that I detect bends and things out there. Now, I'm a meters kind of person. When I did my fiber certifications, we did everything in meters, and I just got used to meters. So the next one is, do you have a launch cable? If you do, great. If you don't, hit no. If you do, ironically, all launch meters, all fiber jumpers and things like that come in meters. You can't buy them in feet or yards or anything else like that. So here's a way to cheat. I tell technicians, hey, if you're a feet kind of person, you can go in here and you can Google, okay, what's my conversion from meters to feet on a 20-meter launch cable, or you can simply click on meters here and put your 20 meters in there, and then if I click on feet, it'll automatically convert it for you. Or I can click on miles if I'm shooting something really long, or kilofeet or kilometers, whatever it is. The next thing is hey, are you using alarms? Most everybody uses our default alarms, but if somebody says, hey, I want you to use one of the TI 568 specs, you can put those in. If you're using one of the older ISO specs, or somebody might say, I have very specific fast pass-fail criteria. I want you to put it in there, so we allow you to do that for users. But usually this is just select your lasers, select your distance unit if you have a launch cable, and go. And I'm going to go ahead and do this and start. And this is going to run, there's my previous one. The very first thing that you're going to see here, it's going to do an auto connection in progress. It's going to try to figure out what the heck I have. It's going to do a connection check. It's going to make sure I clean my jumpers and my connectors. So 1310 just went. Now it's doing a connection check on 1550, and it's done. And so now we've come up into what we call the easy mode. And very first thing you do is you get a pop-up that says, overall, this fiber failed. Gives me the length of the fiber at 5160 kilometers, gives me my total loss at basically 2.7, 2.3 dBs per 1310, 1550. So I'm going to click on that. And now this becomes very simple for technicians to read and understand, and we make it very, very intuitive. Number one, we don't have that trace view. We do, it's on another, I just have to click on it, but we're coming into what we call the smart link view. So now technicians are given smart icons. Now, some of these icons we talked about when I was talking about the trace view a minute ago, but sometimes you might be sitting there saying, well, I don't know what these things are. So the very first one I have up here, I have clicked, it's in purple up here with a yellow on it, and it says, hey, it's a minus 20.42 meters. Remember I told you I had a 20-meter launch cable. Well, when the OTDR measured it, it actually said, hey, it's a negative, it's 20.42 meters. So if I come down here and I click on event diagnostics, it'll just give me a pop-up and says, oh, that thing up there in the far left, that's my OTDR front end connector. If I click on this next one, it comes up and says, that's the end of my launch cable. So now the OTDR has taken into account my 20-meter launch cable. It has set me for 0 meters. So right now this is my starting point. Well, now I've got some green and yellow icons up here. I've got a green icon. I've got a green icon over here. I have a red one. I've got a couple red ones over here. Well, if I click on this red one right here, I click on event diagnostic, it tells me my splice, and it failed. It's saying, hey, this failed the threshold. Well, if I look at this, what I can do, if I look at this overall table here, we have our smart icons up top. In the middle, I have my end-to-end, my link loss, my ORL, my fiber length, and my average loss per dB per kilometer. Now, if I want to see my actual events and what's happening on them, down on the right-hand column here, I have something called Event View. And it clicks up here and it says, oh, my splice loss is too high. And it tells me the distance. It tells me 13, 10, 15, 50. It tells me the loss for each one of those. Remember, I told you a splice 0.05 to 0.1, 0.2. Well, these both are 0.6 and 0.5. So these are bad splices. If I clicked on this green connector right here, it says, hey, it's a 0.160 dB. That's wonderful. Has a reflectance of neg 57.18. Well, if I go back to that chart and it says, hey, UPC connectors are somewhere neg 50, neg 55, or something in the neg 50s, chances are that's a blue UPC connector. If I come out here and I click on this bend right here, it says, hey, this happens to be a bend that's 4.487. Remember, I told you a bend is anywhere from almost 5 to 10 times worse at 1310. But in this case, we measured no loss whatsoever at 1310 and almost 0.5. So there's your 5 times. If I click on the back end of this, it says, hey, there's the end of my fiber. So we have this event view that you can go down and you can actually see all of your numbers, your loss, your reflections, and things like that. Up top, we have all these smart icons, and down at the very bottom, we have one section that's set for alarms. And in this case, it tells me all 3 alarms that are up there. It tells me I have 2 bad splices, one at 1207, one at 3219, and I also have a bend out there at 3977. This makes this very simple for somebody that has not been doing OTDR testing to go out and look at this, and they can say, okay, I can see these different events. I may not know this exactly, but I can look out here and I can say at 3219, I've got a bad splice out there. And if I click on that, it'll highlight it. And down there below, it'll highlight that and say, yep, that's a bad splice. Now, one of the things that we also do is some technicians are more seasoned than other technicians. They like the smart setup, but they're a trace view type of person. So up here in the top right, I can move from smart link view to trace view. Wow, there's my trace view again. So now there's my trace up here. And again, I have a 1 and 2 up here in the top right, which allows me to switch from 1310 to number 1 to 1550. So I'm going to highlight the bend down here at 1310. Or excuse me, at 1550, it's at 3977. And I've got my cursor out here on that. But if I go to event number, if I go to 1310, there's no event out there for 13 because there was no loss. So if I want to come in here and I want to do a quick zoom on that, I can come up here and I can click up here on the top left and on the bottom right, and I can bring that in there, and then I can separate this and expand on this a little bit. And you can see in the blue there, which is 1310 going across there, I have no loss. But I've got that almost 0.5 dB of loss at 1550, which is showing us that, you know, the OTDR now knows that this is a bend. This is not just a bad splice. So hopefully SmartLink Mapper works, makes it very simple for technicians out there, especially if you're new to the OTDRs and you're new to all this. The smart icons make this work really, really well. So I'm going to hand this back over to Mike. You're on there.
Thank you. So let me set up my screen share for you, please. Okay, it should be loading.
There we go.
So Jeff was talking about bands. Many times in the field, technicians will test at 1 wavelength, or they're only required to test at 1 wavelength. Well, if we're testing many fibers, we can compare them. If they're in the same cable, loss, distance should all be very close. So if people do test at just one wavelength, such as 1550, I give them a tip and trick to help them out. If they see something bad, now they can stop and do 2 wavelengths. If it's bad at 1310, it would be bad at 1550. But in this case, we've been shooting at 1 wavelength, and at event 4, I see a splice that's a 1.69 dBs. It's not a red because I did not set alarms, but we would say 1.7 dBs is a bad splice, go resplice. Now we resplice and it comes out as 1.8. We resplice, it comes out as 1.5. So in this case, it's not a bad splice. If we shot at 1310, notice now at that same distance, it says is a bend. So I got the symbol on the trace. If I zoom in, it's a big dip at 1550 and is a little dip at 1310. And if we go to the map can tell us that it's a bend as well. The map didn't work right there because I did a overlay. I got 2 different traces, but this lets us say that this event is a bend instead of trying to fix a perfectly good splice. So if you're trying to save time, you're doing 20 seconds, or quicker, 10 seconds, 10, long span, 30, 30. Once you see something bad, you can go ahead and shoot another trace at both wavelengths and then confirm that it is a bend or that it is indeed a bad splice. The other tip and trick is to get the exact distance. So if we do a trace in real-time mode, this is commonly what we're doing when we splice. We got to splice new fiber to old fiber, so we need to make sure we're on the correct fibers. So I don't have any splice boxes here, so I have some fibers connected together. So every connector, I'm going to pretend is a splice box. And I'm going to short span here, but if you're in a long span, 10, 20, 30, 40, 50 plus miles, or even if it's just 5 miles away, which isn't very long, how do you know exactly where the break is? If the 80-mile span is broke at 50 miles, that doesn't help me much to drive 50 miles and start looking in the woods or the side of the road. So one thing that we can do, if we go about 250 miles, and then we can find a splice, and hey, we're at about 50 miles. Our documentation isn't good. We're just not sure. So we can bend a fiber to try to see where it is. So that's up at the beginning. But in this case, if that was 30 miles, I got to go to the next place. Now, if I bend here, that's out at the end. If I bend here, I can see it dipping. So now we can bend at locations and say where the problem is after a known event. So that helps you to identify. So if this was splice X out there at mile 30, if I bend it, I can see it. I see where it is. Okay, the break isn't there. We can see another splice afterwards. So then we'd be able to go out to the next splice. And now when we bend on that, that's the end of the fiber. And this is right before it. So don't just say it's broke. The 80-mile span is broke 50 miles from here. You can say the 80-mile span is broke 50 miles from here, and it appears to be 1 mile past a known splice point. If you know where that splice point is, then you can go put a bend down there and say, okay, it's definitely a mile from here. You got 100 feet of slack or 50 feet of slack. You take that away, and now though you're on an 80-mile span with a break at mile 50, you know that it's only X distance, which is typically between a splice, so it's not very far, and it just helps you to find the problem a lot faster. Jeff, do you got one more tip and trick to show?
Yeah, I do. I'm going to switch. I'm going to grab control. So one of the things that people come up with when they're out troubleshooting fibers is, again, going back to my, what I call my cheat sheet, is what do my numbers mean? So right now I've got two traces that are overlaid on each other. And somebody says, okay, I'm looking at this trace right here. I know, and if you keep good documentation, I know that this fiber is about 5,200 meters, or a little over 5.2 kilometers out there. So you're like, okay, well, I'm seeing 5182. I'm seeing a neg 63.89 out there. Okay, that tells me it's probably an APC connector and it's plugged in clean. So I'm seeing the end of the fiber out there. I'm actually physically seeing that connector. So sometimes in patch panels and things like that, people, and especially with LC connectors, LC connectors are real, they're not very big. If you don't have the tool, you're going to use your fingers. And if you've got big fingers, sometimes you go to unplug your fiber and you might unplug another fiber. So now all of a sudden the next person's out of business. So if I go over here to the next one and I click on number 2 here, I'm looking at the same exact distance, 1581. I'm looking at a third meter difference, but now I'm a neg 37.9. Well, what did my cheat sheet say? Cheat sheet said an APC connector unplugged open to air is somewhere neg 35 or less. So I could look at this and say, well, my distances are relatively, pretty much exactly the same. I can see, I can see that this fiber is actually unplugged. If I come in here and I zoom in on this, zoom dummy. There we go. Now I zoom in, I can see those spikes right there, the reflections that I have out here, and I've got a very tall, let me move my cursor off over here a little bit, get that off out of the way. So I get that out of the way there. Okay. So now I come back in here and I can see that high reflection of that let me get down to the end here of the neg 37. So I can see that tall reflection. If I come back here to event number 1 where it's plugged in clean, I see that little reflection of neg 63.89. So I see the small reflection, which says, if I looked at that on the OTDR, well, this one appears to be plugged in and plugged in clean. And if I look at this one appears to be just flat out unplugged out there. So hopefully that makes sense. And again, it all comes down to understanding your numbers. If you look there at event number 6 and 7, I've got 2 splices. They both tell me both splices are bad. So I can look at these information, I can look at these numbers, and we can make this cheat sheet available for you. I have it in PDF form, and I always tell technicians, get this cheat sheet of the loss and the reflection numbers, print them back to back in color, take them down to Kinko's or someplace, unless you have a laminator, spend a couple bucks and laminate it. Keep it with your OTDR until you really understand these numbers and they become ingrained in your head and you don't need that cheat sheet anymore. Mike, I'll hand it back over to you.
That's all we have for presentation material. So if you have some questions on OTDR results, finding problems, launch cable length, please go ahead and type them in now. But we do thank you for your time and attendance. Hope we help some of the newer folks out. And if you have been using OTDRs, hopefully it helped. Somebody said, hey, can I go look at total loss and total length without a launch cable? The answer is yes. We just better make sure we're cleaning and scoping. You plug in and the start of that span is dirty with the mud pie. Your OTDR is going to say loss or length 0. It can't see anything. Go get a second OTDR, length 0. There's a mud pie on there. So if you're not going to use a launch cable, you need to protect your OTDR with inspection and cleaning. And if you want your trace to be good and correct, you need to be inspecting your fiber under test. Remember, our OTDR does a connection check. So when we start, it'll say good or bad. I've had people say your OTDR is horrible because it said it's a bad connection. Well, we inspect it, it's filthy, then we clean it up, and we can usually get it to work. There can be permanent damage, and then I say, go get me the other OTDR you use from a vendor that doesn't have connection check, and this is your golden one, this is the one that's great. I inspect it, and it's got a mud pie on there, and it's absolutely filthy. So we tell you, if you plug in clean is good, but if you plug in dirty, it's bad. I haven't seen any other vendors do that yet in the industry.
Yes, yes, Mike, we've got a very interesting question here for you and Jeff. What tool do you use for high density LC jack fields?
So I'm not sure I understand the question, but if it's high density, Jeff's talking about it's hard to reach, our fingers are big, it's in small places. There is a tool, I liken it to like a charcoal grill starter or even a cleaning stick. It's a long device like this. So if it's high density and there's many LCs, people can plug in, grab a LC and plug it out. But if I'm testing LC, it's the same traditional tools. But if I have high density and they're very close and they're hard to get at, look for a LC tool, plug it in, grab it, and pull it out. So I'm not sure if I answered that question, but that was my stab at it.
Yeah, for inspection, we also have some special tips, correct, Mike?
Okay, so thank you. We're saying use a launch cable or not if you know what you're doing, but it's hard to get it with your hand, so there's that tool. But now when you go to inspect, many of the scopes in the industry are short and fat, and if they're high density, with all these LCs sitting side by each other, the common probe is going to smash the guys next to it. So for LC, we have a regular tip, which is short, a long tip, an extra long tip. We have 60-degree angle tips. And then for some new connectors, some specific manufacturers, if you can't reach it with whatever probe you have, and it could be one of ours, contact us and we will have a specialty probe, knowing that stuff is getting smaller and the traditional probe just can't jam in there without jamming the fibers next to it. So a lot of times it's a long tip or extra long tip. It's a new skinny tip, or it's a 60-degree angle tip. So the 60-degree angle tip, if it works with the camera, the tip will go in to this little place and the probe is angled down. So now it's not straight and we're not bashing stuff that's right next to each other. So with our OTDRs, we have our modular OTDRs, the T-Bird 2000, the T-Bird 4000. We have our smart OTDR, which is non-modular, but they can all use short launch cables if we do that multiple pulse. Contractors many times don't do multiple pulse, but if you're a contractor or you're required to do a long shot and a short shot with our smart acquisition advanced feature, then now I can do those both at the same time in one file. So we could be on a 90-mile span with a 20-meter launch cable. Based on this class, we'd say there's a dead zone. You would never see it, but we do a long shot, a short shot, or a long, medium, and short, put them all in one trace and put them all in one map. And then if we go to FTTH Slim, now we can use up to 6 pulse widths, one trace, one map. Our point with mapping is if you do multiple pulse widths, you want to see the actual trace. You got a mud pie in your OTDR, you got a horrible band, you got a dirty connector with bad reflections. If you're producing horrible traces, you get a horrible map. You don't want your map to have a bunch of fake events. So if a span is good, maps are pretty effective, but the span is horrible and there's fake bogus events out there, then the maps get bogus.
Something. Hey, Mike, and Evan, I'm sharing right now my GUI. So when we're talking about OTDRs and things, I went over the smart OTDRs. When it comes to CWDM or DWDM or fiber to the home, we do have a smart wizard OTDR. Instead of having to go into the expert OTDR, you can go in, you can load. This is an option that you can put on there. Again, it makes it very, very simple for you to set up your OTDR without having to go through pages upon pages of options and things that you might or might not get right. So that's one of the things that we put on our 2000s, 4000s, 5800s, things like that. If you're doing those things, we have those applications to make this more intuitive for the technician out there.
And we mentioned those, but we didn't show live traces. You could have a 1x2 splitter, a 1x4, and a 1x8, and the OTDR is going to tell the user, us, the testers, that, hey, it's a 1x2, a 1x4, 1x8. If we go to unbalanced splitters, now it's not a 50-50 split. 90% of the signal goes through, 10% comes out to a drop. We're starting to see that more and more in PON and fiber to the home, especially in rural areas. Our OTDR is going to identify those splitters. So it's a 95.5, a 90.10, a 85.15. And the same way Jeff mentioned it with CWDM or DWDM, you need those wavelengths to go to the system. So it's going to say launch cable, splice, mux, go down the span, see a demux, and see fiber after the demux. So if you're doing CWDM or DWDM, you can't use 13, 10, or 15 OTDR, but now mapping still exists. It's going to tell you mux, demux. So those are a little bit more advanced that we didn't cover too much today on the OTDR basics. And the same way at the cell tower, there was a question about the cell tower. Yes, we can use a short launch cable because the OTDR works. If you have one that doesn't work, you might be required to use 50 meters or 150 meters. But now when we shoot up the tower or up and down the tower, if there's a loop back, now we're going to label it bottom distribution box, top distribution box, RRU1. So now the trace isn't just a connector. We name it with a nomenclature that's actually on the tower.
Hey, Micah, I might just pause you there for a second. Some great information, but we've got two more questions that came in. One is from Paulinus 1973. I have a question regarding launch power at the beginning of the trace. Which value is good and what is bad? Any rule of thumb regarding launch power?
Well, for our OTDR, you as a user and I don't necessarily know what the launch power is. So it's going to come out at a set rate. That's not on the data sheet. We can look it up for you. But what it's going to do is change the pulse width. If it's going really far, it might crank up the launch power. In general, most of the OTDRs come out at 0. So I'm looking at the one on my screen right now. I see it as 0. That's not 0 dBm, that's 0 dB. So your OTDR can be coming out at plus 10 dBm from one manufacturer, 0 from another, maybe -7 from another. But the point is they still can all see down the span. So there's not a setting on ours for launch power. You can pick pulse width. You need more pulse width to go down longer spans. If we put it in automatic, then it gives us the correct setting. Jeff made a sheet, so it gives you different pulse widths, short span, 5 kilometers or less, about 10 nanoseconds. So we do have charts that help people pick. I have a lot of them memorized, but the ones that I don't care. I shoot an automatic. I see the pulse width, and then I can change the manual and modify the pulse width as needed.
Very good, Mike. And one last question. Good connector loss, but low reflectance. What is the issue?
Good connector loss. It said low reflection. Low reflection is actually good. So it would be good connector loss, but bad reflection. So if there's light in the core, dirt in the core, we expect loss and reflection to be bad. If we see one or the other, then commonly the core is good, but there might be some dirt in the cladding. So sometimes it's the other way around as well. Loss is good in the core, but reflection is high. We just did that one. So the other one is loss is high, but reflection is good. So if there's no dirt in the core, reflection is good. But if there's loss just sitting outside of that core in the cladding, then that could change it. So if it's really dirty, it's a bad connector with a dirty connector with bad loss and bad reflection. And sometimes we see one or the other, bad loss, good reflection, or bad reflection, good loss. It just may not be mated properly, might not be plugged in all the way, and it might have dirt outside of the core.
Thanks, Mike. And one more question. This is from Dan. I know you can use real-time OTDR when someone is inside a case trying to find a bend. Are there any other good times to use real-time OTDR?
Sure. A lot of times when I'm out with splicers and things like that, they may be splicing cables and they've got real-time OTDR running as the next person's out there splicing that, and they can actually watch that splice happen and that next section come online as they're moving, from splice point to splice point to splice point. So that's one of the things that I see a lot when I'm out with fiber splicers and things.
And maybe the other possibility is we're not at a splice box, but it's just a way of continuity. So normally for continuity in a long span, I use a source and a meter. On a short span, we use a red light shooter. Now it's a long span, I got an OTDR, but you have no test tools. So I could tell Jeff 50 miles away, I'm gonna go into real-time mode, and Jeff, please bend it. Well, then I'm gonna see the drop, and I'm gonna say, okay, Jeff, I'm on fiber 1, what are you on? He's like, I'm on fiber 12. Well, you guys wired it backwards. So that would be another possibility on a long span where you want to use it for a continuity test. You can tell by that bend that we're on the right fiber.
Perfect. Thanks, Mike and Jeff. Doesn't look to be any other questions at the moment.
Thank you all very much for attending. I hope you picked up some tips and tricks and some knowledge on this.
And again, if anybody wanted that handout that Jeff has put together, his email is in the chat, so please feel free to reach out to him. And as always, we're here at VIAVI to help you out, so don't feel that you can't contact us for any of the technical questions. Thank you.
So we covered basics today, but we mentioned CWDM, we mentioned DWDM, we mentioned FTTH, we mentioned cell tower. So cell tower, we still got your, it's not old per se, but 4G LTE. We got 5G, which is certainly new. So if there's any specific topics, be it technology or product, we see more and more new people handling fiber. So we think inspection classes are old. We say inspect before you connect at VIAVI, IBYC. So we'll go out there thinking we don't got to talk about IBYC. There's a lot of new people and we still have old, bad habits. Network's not working, testers aren't working simply because there's dirt. So if folks need a new IBYC class, which is in theory old material, but so many new techs, it's still vital. So if you're senior or you're new, let us know if you want to see some other topics. And then we try to stay away from PowerPoint nowadays. We use it for some theory, but we either did live shots today or we loaded traces. So instead of going to the PowerPoint, we're trying to use more camera, more screenshots, and more actual live tests.
Thank you all very much for attending.
Thank you all indeed. Be safe and stay safe. Thank you.